Okay, so in our last video, we talked a little bit about the Born-Haber cycle and what we were doing with with lattice energy. So just as a quick recap, okay, so we have Born-Haber, or the Born-Haber cycle, as we call it, all right? And we're going to use this basically to find the total amount of energy required to break up an ionic, basically an ionic compound into its constituent ions, okay? So we're basically going to be finding the lattice energy, okay? Now, important thing to note is that if you have an ionic compound XY, all right, that will be a solid. If you're using lattice energy, you're going to be breaking this down into X minus gas plus Y plus, or actually this should be X plus gas, Y minus gas, okay? So you want to get these in the gas form, okay, or the gaseous forms, okay? So in this question, all right, and I'm going to put the question in the description, it's going to say the enthalpy of formation of rubidium chloride is negative 430.5 kilojoules per mole. The enthalpy of sublimation of rubidium is 86 kilojoules per mole. The first ionization energy of rubidium is 402 kilojoules per mole. Bond dissociation energy of chlorine gas is 243 kilojoules per mole. And the electron affinity of chlorine is going to be 349 kilojoules per mole. So let's find the lattice energy, okay? So unlike, previous Hess's law problems, as I've said in the last video, we're not given these equations explicitly. We have to derive them from the information that we're given, okay? So the first piece of information we're given is that the enthalpy of formation of RbCl is negative 400 and, let me bring this down, is negative 430.5 kilojoules per mole. Okay, so what do we mean by that? Like, what does that even mean? Let me actually draw a line here so I know that actually, the line should be like this to know where the edge is. Anyway, I'll just draw a dot here. Okay, so, what does this mean? How do we translate this into an equation we can use for something like Hess's law? Well, what they're really saying, okay, we learned about enthalpy of formation, right? It's basically we have this compound, okay, and it's formed from the most basic elemental forms of its constituent parts, okay? So we have rubidium and we have chlorine. Well, okay, so the first part is easy, rubidium. Well, rubidium in its basic elemental form is found as a solid, and it's found as one rubidium, okay? Well, what about chlorine? Chlorine is actually a gas, right? But more importantly, it's Cl2 gas, right? It's not Cl gas, it's Cl2 gas, okay? And we're going to get our RbCl. Now, you guys should see a problem straight off the bat here, okay? Which is that, all right, well, we have Rb solid plus Cl2 gas, all right? But how many chlorines do we have here? Is this a balanced equation? No, it isn't, because we only have one chlorine here, but we have two here. So let's actually change this to 1/2 chlorine gas turns into rubidium chloride. That's, of course, with a rubidium solid, okay? And it gives us over here, this is our delta H, right? So we can say then that delta H is equal to negative 430.5 kilojoules per mole. Okay, I know it's looking a little crazy. I need to learn how to write a little bit smaller with a thick marker. Okay, so the second piece of information, this is one, okay, the second piece of information is that the enthalpy of sublimation. So I guess I'll just write this as enthalpy of sub, okay, that's subscript sub, of rubidium is 86 kilojoules per mole. So what they're really saying here is, okay, the sublimation of something means that you're going from a solid state, all right, to a gaseous state, but you're not really worrying about the liquid state. It doesn't really pass through that liquid state. So in this case, here I have rubidium solid turns into rubidium gas. All right, and over here I know then that my delta H is going to be equal to 86 kilojoules per mole. The third piece of information, that was two here, the third piece of information I'm given here, all right, and this is still a little wonky, I have to really get the hang of this. Third piece of information here I'm given is my first ionization energy, so that's IE1 of rubidium is 402 kilojoules per mole. So how do I do that? Well, ionization energy is when you're basically, it's the amount of energy required to pull away an electron from an atom in its gaseous form. So, basically I started off with, let's say, rubidium gas, okay, because it's, again, in gaseous form, okay? Rubidium gas, well, I'm going to pull away an electron, okay? So what I'm really going to say is, well, okay, well, I created a rubidium cation, and that's going to also be in gaseous form, but I'm also ripping away one of the electrons here. And the total change in enthalpy is going to be, over here, I said it was 243. No, 402. Okay? The fourth piece of information, don't worry, we only have this in the next one. The fourth one, and I should write down rubidium here, just so you guys know. Okay? Fourth piece of information we're given is bond dissociation, so this is bond dissociation of Cl2, right, gas. Okay? So what do we mean by bond dissociation? Well, we mean we're breaking down the bonds, right? And here we have, you know, if we were to write this out, and I'm not going to put in the valence electrons, but you can imagine we have two Cl atoms here that are linked by this bond here. We're going to break that bond. So what we're actually saying, if we were to write this out, is an equation. So we started with Cl2 gas. But then we said, you know, we don't want you to be Cl2 gas anymore. We want you to be now 2 Cls, right? So you can write this in as 2Cl. Okay, so let me erase that, make that a little bit more clear. Gas. Okay? And finally, our last piece of information here is going to be, all right, well, we have an electron affinity of Cl. All right, so this is electron affinity 1 of Cl. And that's going to be 349 kilojoules per mole. So if we take Cl, and if we take Cl gas, okay, if we were to take one atom of chlorine in the gaseous form, and we were to then say, all right, we have this electron, well, it'll turn into Cl negative gas. Okay, so these are going to be all the equations we're going to be working with, all right? It's quite a bit. Let me try to actually make it so that way you can see all of them at once. So here's one of them up here. This is the first one. Here is our second one. Here's our third one. Here's our fourth one. Finally, our fifth one, okay? So how do we basically deal with something like... How basically do we use all of those all together? So let me make another video on another sheet of paper in order to make that clear.